Thank you. Yeah, don't worry. You can watch the video on YouTube. Anybody else that's listening, I upload all these videos to YouTube after. Um, so yeah, you can check the YouTube later if you want. If you will miss right now. And oh, I'm already recording. Okay. All right. So let's get started. Oh, I'm already here. Okay. So yeah, let me get rid of this. I always want to play the music, but then it always distracts me. So, right. So this is our little research session. I've been thinking about this problem all day, basically. I'm probably gonna have some people call in eventually, as well. Let me make sure the volume is good on here. So let me just remind what's going on with the problem. Also, I just bought a bunch of new markers, so should be good on markers for quite a while. Yeah, fun stuff. Yeah, so mainly the problem is about this graph homology problem or complex. So this was this double complex. So yeah, let me just summarize the problem a little bit for those who haven't seen. Yeah, new markers. So what are we trying to solve? We have this graph homology problem. And what is the problem we want to compute? The homology group's coming from this certain complex. So essentially, we take a bunch of Cartesian products of whatever the simplicial set is, and we start throwing out these diagonal parts, and that corresponds to diagonal maps. So there's a bunch of these like diagonal maps where we have some number of Cartesian products. Let's just say it's like 2. And I can copy the first component into the third component, so that will be some map that I can denote delta 1, 3, and that maps into here. Okay, and yeah, so what are these things? These are chain complexes, right? So if I have a simplicial set, I can take the Cartesian product of it with itself, and then I can look at the chains on that space. And yeah, so there's this, basically all these things we can create from all these different delta maps, and also within each of one of these, there's something called the Xi homotopy. Which raises degree by 1. And it's, a homotopy is like something that's like a deformation or something that's like connecting 2 different points. So the points that this is connecting is, or quote unquote points, are if I take these 3 Cartesian products and I apply this Alexander-Whitney map and I break it into tensor products. So there's this certain map called Alexander-Whitney. I can break this into some number of tensor products, however many Cartesian factors I have here. And yeah, so there's basically a lot of these maps that come into play for this problem. There's all these different delta maps. There's a Xi homotopy for each number of factors I have here. There's also an Alexander-Whitney map for every number of factors. I'm leaving out a couple other ones too. There's like a Eilenberg-McLean map as well. This is a map from if you take tensor products, it goes the other way. So this goes backwards, back into the Cartesian products. So yeah, there's like a lot of different maps going on, and essentially there's this perturbation lemma that says I can take everything that's going on in this Cartesian space, and I can kind of compress it down using this Alexander-Whitney map into tensor products, but I lose some information. So there's like all these correcting maps that I'm trying to basically define in terms of these surjection operations. Okay. Right. So that's sort of the outline of the problem. I'm not sure if Stuckey's here yet, but Stuckey, I think, said that they just got home, and so they'll probably call in eventually. Also, Kyler, I don't know if they're around, but if Kyler, if you're in the chat, let me know. So yeah, that's the main problem. We have this, we have a bunch of these delta maps, Xi homotopy, and then at the very end, we're compressing everything down into tensor products. And the problem is essentially asking, can we write down all the correction maps? So when we do this compression, we lose information, and then there's a bunch of correcting terms, and yeah. So the main question is, so can we write down the correction terms as surjection operations? Okay, so we're essentially trying to come up with a calculus, or I mean, I already came up with it, but we want to prove that the calculus that I came up with, the way of computing these surjections, is actually correct. So we have to go through the whole perturbation lemma, and it says like, okay, we can do what we were doing on these Cartesian factors. I can push everything to tensor products, but like I was saying, yeah, there's all this correction stuff. So how do we get to surjections is kind of like the whole problem, basically. Okay, Stuckey's hanging out. Yeah, so anybody that wants to call in and talk about this, you know, if you don't feel comfortable, of course, you don't have to, but yeah, this is the 5th time I've done this, so I'm sort of almost at the edge of everything that I essentially know how to do already, so everything else is kind of just speculation at this point. I've prepared a little bit, but yeah, let me get as far as, let me just write this diagram up here. So the general picture for everything I was just explaining here, let me write a better picture. But yeah, any questions? Just fire them off whenever they come up. So maybe I should list carefully like all the tools first that we're including here. So there's a lot of different maps here. There's yeah, let me kind of summarize again. So we have delta maps. On this side, this is Cartesian powers. So delta maps, there's Xi maps. We could also throw in some like rotations here if we want. Although the rotations don't show up for the stuff that purely comes from the graph homology stuff, but for the conjecture one I came up with, you can throw rotations in there. So I guess to be fully general, say we can also do rotations. And then finally at the end, there's this Alexander-Whitney map. And I think that's basically everything. And then everything that we can do to the Cartesian powers, there's this sort of, on the operator side, there's like an analogous map. In the sense that when I compose whatever composition of these I do, if I just replace them with their analogous map, I get something that's important on this side. So this is like on the operator side, or operad side, I guess you could say. So here, I guess I'll just give this another name. It's very, it's related to this delta map, but it's obviously operating on a different space. So this is, I don't know. In the notes, I call this delta up because it's operating on this like BE up operad that I made up, which is like an upgraded version of that one I was explaining a couple lectures ago when it was like the one that's made out of tuples of permutations. Okay, so no questions, everything. Yeah, so we have delta maps which create new Cartesian factors. We have the delta maps on the operad side that basically operate on these like BE things, which I can explain again in a little bit. There's an operator she map, which I'll just call like big H, or operad she. Which is like something I kind of invented, which is obviously related to this she map. Rotations work basically the way you would expect them to on this side as well. And then instead of Alexander Whitney at the end, on the operatic side, we're dealing with these Barrat-Eccles elements, which are the tuples of permutations, and there's a table reduction map to surjections. So instead of applying Alexander Whitney map and getting the action or the coaction of this thing, this is like on the operatic side. What is the thing that's coacting? So yeah, here we're just taking a table reduction. Well, first, because these are upgraded elements, there's like some of them are in partitions, so I need to like unpartition them and just view them as regular BE elements, and then I can take a table reduction. So I can just write it like that. So this is like that. I called it detuppling, but it's really like a linearization map, or like I don't know how to say it. Like instead of having permutations of partitions, you just view them as regular permutations. Like you could have 1, 2 as a single partition, and then 3 as another partition. That could be one permutation, and then you could have like 3, 1, 2, like that. So there's only 2 partitions here. It's 2 permutations of 2 partitions. But you can view this as an element in like Barrat-Eccles 3, where this is just the permutation 1, 2, 3, and this is 3, 1, 2. So you can kind of forget about the partition information, and that's what this map is doing. So this is like forget partition info. Right, so you forget about all the partition information, you just view it as a normal element, and then you can take its table reduction. Right, so that's just kind of summarizing what the tools are, and then like I was saying, there's this, like you want to view these as somehow like linked together. So whenever I do like a she map on these Cartesian products, I can just as easily take this she map on the operator stuff. Rotations, they basically, whenever I do a rotation here, I can do a rotation here, same thing. And then at the end, it's saying, whatever I'm going to get after Alexander Whitney, it should be the same thing as the coaction of whatever is going on this side with this table reduction of this thing. So these are linked together too. Right, so the question is, we can compute all this stuff very easily, but trying to write down what's happening over here is a little bit confusing. So we basically want a proof that says I can forget about all this stuff, do all the operations over here, and then at the end, we want to prove that once I take the Alexander Whitney map at the end, I get the same thing as the coaction of whatever this table reduction gives us. So yeah, let me just draw, before I go on, does anybody have any questions about any of these maps? I know I haven't maybe like fully formally define them, but the delta maps are pretty straightforward. They just create like new copies of things. I guess the Xi map is a little bit confusing, but I did go over it for the Cartesian power side, and this is kind of analogous. So there's a very like close relationship between these two. Rotations, those are pretty straightforward. You just do the rotation like you would do. Here you have like a bunch of elements, so you can rotate them. Like you can see how permutations would act on these. The only thing is that if a permutation acts on a partition and two things get permuted inside a partition, I need to keep them in the like lowest to highest ordering. So for instance, like 1, 2 could act on this thing, but it wouldn't do anything because 1, 2 just switches these, but these are in the same partition, so they don't actually switch. So yeah, rotations act on these things, but unless they're like partitions of one thing, then there's something to do with the freeness is kind of off. In the sense that like you can have 1, 2 act on this and it acts trivially. Okay. Right. So yeah. So what is the map we're trying to dissect? I'm going to draw basically a giant diagram that's going to consist of all these different maps. Keep stepping on something. Right. So graph homology complex basically says we start out with just one copy. I'm just drawing it at the bottom. I guess this is kind of just for aesthetic purposes. There's no reason it needs to be at the bottom. So yeah, we're gonna apply a bunch of these composition like delta maps, Xi homotopy, more delta maps, and then finally AW at the end. So it's going to be a bunch of composition of maps. Finally, we're going to end up in C star M times M times M, some number of times. And then we'll apply Alexander Whitney at the end to get... I just want to write I want to be fully proper, so I'm writing the coefficients here, R. Even though we probably don't have to write that, but okay. Let's say there's n copies here. Okay, so this is basically every time we have a sequence of edge collapses in the graph for the graph homology complex, we get some composition of delta maps, and the h's in between, that just comes from the perturbation lemma. It says that we can do the differential one time, and then all the higher correcting maps come from doing the differential, then applying the Xi homotopy, then doing another differential, then applying another homotopy, and basically you continue doing that some number of times. So yeah. Basically, the deltas here come from the edge collapses. Which is the differential coming from the graph homology complex, the double complex that computes the homology we want. So a single delta is coming from the differential in the original graph, but once you do the perturbation lemma, it says you need to do one differential, then apply a homotopy, then do another differential to get a higher correcting term, and you need to basically keep doing that. So the deltas come from the edge collapses, which is the differential map. Right, so a single edge collapse is like one differential, and then if I do an edge collapse and then do a homotopy and then do another edge collapse, that's like one of the correcting terms, and then I'll have an even higher correcting term if I do one edge collapse, then a homotopy, then another edge collapse, then another homotopy, then a third edge collapse, and then AW at the end. That should be another higher correcting term, and basically you have infinitely many of these higher correction terms. You just have to keep collapsing edges of the graph, basically. Okay, yeah, let me hydrate. Good call. I'm not getting a lot of questions, so I'm assuming everybody's pretty lost, but yeah, I mean, questions might help. It might help me because, you know, like I said, I don't 100% know what I'm talking about, so if you ask a question and something I'm saying is not clear, it's possible that it's because I'm just not making any sense, right? But I think this all makes sense so far, right? I start out with one copy of M. I basically create new copies. Every time I apply a delta map, I get one more copy of M. When I apply a Xi homotopy, that just changes the degree by one, but I don't get any more copies of M. And so basically every time I apply delta, I get one more copy. So this would be like after n minus 1 delta maps and n minus 2 Xi homotopies. So this is all going to change degree by n minus 2. Yeah. So basically, yeah. And yeah, I don't want to say too much without saying something wrong. So this is the composition of all these maps, which I'm kind of being vague here with this, you know, this bubble thing. But there's a bunch of composition of maps here that include compositions of these things without AW, obviously. We just do AW at the end. But then there's another route we can take, which was, I can basically view this thing as being, well, I can view this as essentially the same thing as C star of M and tensored with, how did I want to write this? So I wrote it as like BE of 1, but it's really just like a point. Or it's really C star of a point. Yeah, maybe I should be careful. Right, because the homology of a point basically, like when you take a Cartesian product with a point, you're not changing the simplicial structure at all, really. So you can always view every chain complex as basically tensor product with like the chain complex of a point. Yeah. And the point of this point right here is that it basically is going to expand with the deltas along with the same sort of maps that we applied to get to here. So instead of increasing the number of factors in M each time, we're going to be creating new things in this point. So this point is basically going to expand into partitions, essentially. And then once we apply the Xi homotopies, we're going to end up getting tuples of partition permutations. And that's what I call this like upgraded BE thing. So I'm just going to call this, it's like the Barrat-Eccles operad, but it also has partition information in it. So I'll just call it BE up. And so here we'll have n things to go along with the n over here, the n copies. And essentially we're going to get something similar here, but instead of compositions of these things, we're going to have compositions of the things that I erased on the board before. So we have like the operatic delta, the delta up, the capital H, which is the operatic Xi, and then instead of AW, we have this table reduction of the permutations, or of the BE elements. Right, so we have all this composition here, very similarly, everything analogous to the same thing that we're composing over here, except now instead of delta, there's delta up, instead of little h, there's capital H, instead of AW at the end, we're going to get have a table reduction map. So basically this thing on the left here doesn't do anything. So over here we're creating copies of the m's, creating new m's, and there's no coefficient thing over here. Over here we're not touching the m's on the left, we're just delta and h'ing the stuff on the right, and we end up with stuff in here. And then at the end we apply table reduction, and then we apply whatever we apply the coaction of the table reduction. Whatever we get in the table reduction, this is a bunch of surjections, and we have a coaction of surjections on some sigma in here. And when you take sigma in here, you table reduction, you have some coaction, you get a bunch of tensor factors. So the big conjecture is basically that this whole diagram commutes, right? That I can go this way using these maps and then apply Alexander-Whitney at the end to end up here, or I can go this way applying all these operatic versions of these maps, and then at the end I can apply table reduction and then apply the coaction map to sigma, and I should get the same stuff in the tensor products. So it commutes. So the only thing I'm being vague about is essentially what exactly this composition is, but it can essentially be any composition of these delta and Xi maps. As long as you do the same composition over here, the theorem is that this whole thing should commute no matter what. As long as you, like I said, as long as you use the same maps on both sides, or the analogous maps. Yeah. So the tough part here that I was going over before I started streaming today was I was thinking about what could if there was a possible map that related these two before we apply Alexander-Whitney. So this is a big question mark here. Maybe we'll figure this out for next week. But this hypothetical map I'm calling psi n. And I believe there's a map here that sort of translates all of this information up to this point before we apply Alexander-Whitney from the operatic side. So I can go basically shortcut before this, go to here. And then the theorem would be to prove that this commutes before we go to Alexander-Whitney. So yeah, I can write down a couple proof ideas in a second. It'd be nice to label what each letter is on the sideboard. Oh, you're talking about these? Yeah, I just erased it. So yeah, just to go over it again real quick, the deltas, they create copies of the Cartesian factors. So if I take like delta 1, 2, I can create a copy of whatever's in M. So some sigma, some simplex in M. I can create 2 of them, and now it's in M times M. And then when I have 2 of them, I can create 3 of them with another delta, and I can keep doing this until I end up in here. And every time in between, there's going to be this Xi homotopy map, and that just comes from the perturbation lemma. So there's deltas from the edge collapses, that's the normal differential, and then this H comes from the perturbation lemma. And the perturbation lemma again says that if I want to shift from some big complex to a smaller complex, I can project down, and that's what we do with this Alexander-Whitney map, but I need a bunch of correcting terms, and how do I get the correcting terms? I just need to apply the differential a bunch of times, multiple times, and in between I need to throw in the homotopy. I'm glad it looks like that cutoff thing works. I wouldn't be super thrilled if the collapsing only happens at the very end. What do you mean by that exactly? Super thrilled with the collapsing only happened at the very end. Yeah, I'm a little confused what you mean. Oh, I think I see it. Like the fact that this map here exists, or so this is the thing I've been trying to like define. I feel like I know what it should be, but there's a little bit of ambiguity going on with what's going on over here, which makes this also ambiguous. So I can go over that in a little bit. Yeah, existence of psi. Yeah. So yeah, that's the thing that I think. So let me go over the proof idea that I had written down here. If we can figure out what this psi n should be that makes this also commute, then I think we're good. Then I think it's a simple proof because, well, depending on how complicated, but I think I know what this psi n should be, and if we can prove what it should be and that this intermediate map diagram commutes, then the only thing we'll have to prove at the end is that this top thing commutes, that I can go here first, then apply Alexander-Whitney, or I can just take the table reduction and I should get the same thing. So it should be like an inductive proof where we prove that, you know, up to the n-1 step, the diagram does commute. We'll just assume that we'll just assume that for induction, and then somehow I'm assuming that we'll be able to prove it at the n step. And then it'll be a two-part proof, so we need to prove that this intermediate part commutes, and then we also need to prove that this top diagram commutes, basically. So it's like two diagrams stuck together, and we need to show both of them commute, basically. So yeah, that was my idea. I'll write that down in a second, but yeah, any questions about this diagram before I erase it? So there's I like to just call it like the Cartesian stuff. So all the maps that involve the Cartesian powers going up to here. And then there's the analogous composition of maps, but on the operatic side where we end up in this space. And then there's this magical map that we have yet to define, but the theorem would first be to prove that, so I can go up here or I can go here and then across here, and it should be the same thing. So this intermediate diagram commutes, and then separately we'll show that I can go here and then Alexander-Whitney, or I can just take the table reduction and apply the coaction. And that will be the same thing. In defense says, so there are no guarantee that there are more commuting diagrams within the three dots. Well, actually, yeah, there is. So I'm leaving out stuff. Yeah, there should be a level at n-1 as well, and a level at n-2. And so yeah, the full diagram I drew in my notes is a little bit larger, but there's not so much room on the board. So. But yeah, there's a lot of stuff that I'm leaving out that would also commute. There's like all these intermediate maps as well. There'd be a psi at n-1, psi n-2, and etc. Also, there's a whole like other side of this diagram. There'd be like another vertical layer that I'm not drawing, which I don't want to go into yet, but there's really like 3 levels. So this would be like one vertical level. This would be another, and I'm leaving out one that's not super important yet, but maybe we'll need to prove like later. Okay, any questions? Yeah, so existence of psi, this is what I want to basically focus on. This is, if we can find a good psi n map here that makes this stuff commute, I believe then showing that this stuff commutes is probably not so hard. So yeah, trying to pick the psi n to make this work. So let me just write down that. So if we did get that map, then the proof would just look like it would be a two-step proof. So first, we would have to show that I'll just call this delta nh, little h. So the little h means you know it's in the Cartesian space. So this is basically that dot 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 air bubble I wrote before. Like, this is the composition of all those maps. So I'll just say, like, this is, just to be very informal, this is the three circles that I had before. And remember, the three circles brought us from like 1 factor to n factors, right? Of course, like C star, right? Yeah, blah, blah, blah. So this thing takes us from 1 factor to n factors and applies a bunch of h's in between. So this, shifts degree by n plus n minus 2. So first we want to show that this is the composition of that psi n map and the operatic stuff, which I'll write like that. So basically, this is saying that first circle commutes, right? So proving that first diagram commutes, and then separately, we can show that, or we want to show that the Alexander-Whitney map of the psi n of, now I plug in a simplex here. This should be the same thing as the table reduction of psi of that simplex. Right, so there's a coaction, right, for surjections on the simplex, and so this is basically just, but this is just restating what I had before. This is just saying that the first diagram commutes the smaller diagram from the bottom to the intermediate part, and then this is just saying that the top part of the diagram commutes. So essentially just restating the commutativity of the last diagram. Well, this is like two of the equalities that you would get from that last diagram commuting. Right, so this is just saying you can do all the operatic stuff, then apply this magical psi n that we haven't defined yet to end up in the Cartesian factors, and then that should be the same thing as if I just did all of the operatic stuff, or sorry, if I did all of the deltas and little h's on the Cartesian side, it should be the same thing. So psi should be basically like a dictionary or a translation mechanism that translates the operatic information into the Cartesian stuff, but doesn't lose any information about what the coaction is, in the sense that I can just apply the table reduction map, and that's the coaction that we get. So that's what the second this second part says. So first part says that if I want to know what's happening on the Cartesian side, I can just do all the operatic stuff and then apply this psi n. And then the second one's saying if I want to know what happened after AW when I go to psi n, well, I don't actually have to go to psi n. I can just take the table reduction of everything that I had beforehand, basically. So 1 and 2 together, if we prove 1 and 2, then they both imply that exactly what we want to prove, basically, that the Alexander-Whitney map of delta n, or delta h, little h, of sigma, right? This is the thing that we're trying to figure out what it is. But 1 and 2 says, okay, we know what it is. It's just the table reduction of this forgetful map, and then the operatic stuff, big H, and then plug in sigma. And yeah, I mean, I think this is just straightforward from 1 and 2, right? This is, yeah, just plot, yeah, 1 says this is equal to this, and then 2 says if I apply AW after this, then I just get the table reduction. So if I combine those two, it says, okay, it's just table reduction of that. And that should be this. M is any R module. I think it's only important in the sense that it's the place where the sigmas live. Sorry. So M is not an R module itself. C star of M is an R module. It's actually a DG R module. So really, I shouldn't say M here. This is really like, should really say like C star of M. And then this goes to n factors, but it also shifts degree by n minus 2. Yeah, and really I'm leaving out the like colon R part, but that's just the coefficient ring, right? And every time I write tensor product, it's actually a tensor product over R. I'm leaving that out also. That's just shorthand notation. So like if I have one chain complex and I write tensor B, and we're dealing with coefficients in R, this is really tensor product over R. I'm just like so used to not writing it. So yeah, all tensor products are over R, and anytime I write like, yeah, all tensor products are over R. Oops, probably shouldn't erase that. Any questions? So yeah, M itself is not an R module, but C star of M is an R module, and obviously C star of M times M times M is also an R module. Well, if it's with coefficients in R. Yeah, so this is an R module. R is any ring or K algebra? Yeah, R is just any commutative ring. It has to be commutative or else the tensor products. Yeah, you have a problem with tensor products because if the ring is not commutative, then when you take the tensor product of two modules, first of all, it needs to be like the first one needs to be a right module, and then the second one needs to be a left module, and then when you take the tensor product, it's no longer an R module. It's just like an abelian group, I think. Yeah, so the standard ring is Z. So just anytime you see R, just think of integers. So, and the integers are like the standard one, like Stuckey says that we want to calculate it for because integers are a good example because they're a commutative ring, but they don't have, there's no inverses. Except for, 1 and -1, of course. Right, so this is my idea for the proof. Essentially, we would prove these separately. So we need to define this psi n first. All of the other stuff is already defined. All the stuff that goes into these two maps. So then it would just be a matter of just proving this by hand. I think we can prove this by induction. Maybe assume it's true for at the n-1 step, and then try to prove it for n at n, and then prove it for n plus 1. Happy Saturday. Hey, Zach. Yeah, so, yeah, just banging our head against the board trying to make some progress on this problem. I've sort of been thinking all day about this psi n map, which if we had a nice definition for it that made this theorem true and we could prove it, then that would probably make things a lot easier. Then we could probably just prove 1 and then prove 2, and then they should imply the theorem that we want, which is this statement at the end. So yeah, basically trying to brainstorm what should this psi n map be. I can go into a little bit more detail about like what we think it might be, or like how it might behave, or how we might get to what this should be, but right. Okay, so now what is C star? A chain or something? Yeah, so C star is a chain complex. So anytime I have a simplicial set, which M is the simplicial set, and if I have a simplicial set, then Cartesian product of two simplicial sets is also a simplicial set. So anytime we have a simplicial set, I can look at the chain complex based on that simplicial set with some coefficient ring, which is commutative. And this is just basically, I take a free module of all the k simplices, which are like k-dimensional triangles in the space. And you have all these relations between all the vertices and all the edges and stuff. And that's all stored in this differential map that's on the chain complex, which basically is like a boundary map that takes every simplex and sends it to its boundary. So yeah, you can learn more about this if you look up like chain complexes with coefficients in a ring or anything related to that stuff, simplicial sets, stuff like that. Right. So basically this cyan map I think is the crux of the problem. I've defined, in my thesis, I talk about these things called A configurations, which I basically are just some mathematical device I made up for my thesis. But I have like a map, I have a cyan map that makes sense, but it gives us like the wrong things. But weirdly enough, I think after you apply the Alexander-Whitney map at the end, you actually get the correct answer. So it's a little bit weird. So I have like an A configuration version of this, but it actually doesn't give us the right thing. So I have maybe like an altered map. Maybe you could call it like cyan tilde or something, where you basically do everything that you did before, but then there's this map that gives you A configurations, and then when you apply the Alexander-Whitney map of these A configurations, you actually do, in my opinion, I think in my conjecture, it would, I'm conjecturing this, but it seems like from everything I've checked, it seems to be true that when you take these A configurations from my thesis and you apply the Alexander-Whitney map, you actually end up getting the correct surjections in the end. So it's kind of a little bit of a weird thing. I can sort of like, I have some intuition on like why it gives you the correct answer, but it's also like not super clear. I mean, if it was clear, then it's probably just as clear as the full problem. So it's not exactly obvious if I got anywhere by this A configuration stuff, because it actually, if I apply the A configurations, then this equality actually doesn't hold, like on the nose. But whatever you get, you apply Alexander-Whitney, it's like somehow the difference is in the kernel of the Alexander-Whitney map. So there's like something weird going on that I don't really fully understand. But okay, what am I missing here? So it collapses to whatever boundary it has. The delta n. No. So the delta n map, that doesn't have to do with the boundary. The boundary map, usually we'll write it as like differential. So like if you have a triangle, sorry, I guess the triangle and the delta is going to be confusing. Let's just take a single line, right? You have a line here, you have point 0, you have point 1. You apply the differential map to this, it'll send it to the point 1 minus the point at 0. So it's like one point minus another point. And remember, this thing is made up of a free abelian group on the set of points or edges or, higher dimensional simplices. So you're basically getting the boundary, right? Because if I have this line, the boundary of the line is, one of the vertices and minus the other vertice. And the minus just has to do with, there's some sort of orientation here, meaning that like 1 is in the front and 0 is in the back. That's why the 0 gets a minus. But yeah, in general, you can have like a triangle, you take the differential, you get the boundary of the triangle. If you have a tetrahedron, you take the differential, you get the two-dimensional boundary of the tetrahedron. And there's also a thing where if you take the boundary twice, if you take the boundary of a boundary, then you actually get 0. So if you take the boundary of something and you get 0, that means it was like this, it was a closed loop in some sense, or it was like closed, it was already enclosing a space, and when you took the differential, you got 0. So, and you can see that here. If I take the differential of this, well, the differential on each point is already 0, so it's just 0 minus 0, but yeah, that's not a good example. I guess you'd have to go up to 2 dimensions to see the first non-trivial example. But Whitney embedding. What is the Whitney embedding? Oh, this is similar to chromatic yeah, very much related to chromatic polynomials for sure. Yeah. Yeah, the graph homology complex itself is related to the chromatic polynomial. Yeah, there's this whole story I was telling in the first or second lecture about if the ring is like commutative, then the graph homology basically is giving you the same stuff as the chromatic polynomial stuff. But there's like this Euler characteristic that translates between the two, but yeah. Okay, so I still have everyone. So yeah, basically I'm just trying to brainstorm like what this cyan should be. And if we can get a good information on that, or if this cyan is like too hard to deal with, then maybe there is some way to save the A configuration stuff and I can translate everything into A configurations, and when I take the Alexander-Whitney of those, we have to basically prove that we haven't changed anything. So this is one way. Try to define this cyan so that this is equal on the nose, and then try to prove theorem 2, and then they'll both imply what we want. Or if we can't do that, if that's too complicated for some reason, or if we can't define this cyan easily enough, then I have another route, which is this A configuration map. So we either have cyan on the nose exists as a map that we can write down easily. So either we figure out the map cyan, which makes this whole thing commute. Cyan should be going into yeah, so cyan is taking something here, tensor BE upgraded. Yeah, I'll just write N. So either we figure out what this map should be that makes that whole thing commute, that makes the diagram commute. Commute exactly. Or maybe trying to get that diagram to commute exactly is maybe too much to hope for, and maybe we maybe I can recover it with some secondary method using these A configurations. And I'll call this like a cyan tilde map. So it's from the same space. I'll just call this like A or something, so I don't have to rewrite it. So operating on the same stuff, but it's not going to give us exactly what we want. So it doesn't make the diagram commute exactly. So it doesn't make it commute exactly, but whatever I get at the end, when I apply Alexander-Whitney, somehow magically I get the correct answer. Or in other words, that the difference between these two maps is in the kernel of the Alexander-Whitney map. So I think this is true. I'm just not so sure of how easy it is to prove. So that the kernel of, I need to be careful about what is the thing that we're, but basically So I'm writing down two different ways to do the same thing essentially, like two different maps, but they're not exactly the same map. One we're getting A configurations, and one we're actually getting like the exact thing we should be getting. And then it would be a separate proof to show whatever the difference is between these two maps. When I apply the Alexander-Whitney on the coaction, then it's in the kernel. So it's in the kernel of. I just need to think about how to state this. But yeah, just to summarize, so it's a map from the same space to here, same map between the same spaces. This one I know how to define though, that's the difference. This one is like theoretical that I think it should exist. Oh, I thought that was someone else. Hey, hello. You had the same color in the chat as Stooky, so I thought that was Stooky saying hi. But yeah, hello. Yep, we're doing some research here. Welcome to the chat. So yeah, I think it's similar to a lot of this problem. Seems to be there's a lot of different ways to view it that are like equivalent, or maybe they're not exactly equivalent, but once you apply the Alexander-Whitney map at the end, it erases whatever the difference was. So that's what I think is going on here. There's like the literal map where this is, once we apply this is exactly what we should be getting through this composition of all the deltas and chi's. Or maybe it's not so easy to define this map, or I have hope for this though. I think this should be able to be defined. But if going down that route is a little bit too hard, then I already know that this map is well defined. This has a very similar mapping, and then we just have to show whatever the difference is between this and the exact map. It just gets killed in the end. So once we apply Alexander-Whitney, yeah. So this map, you apply Alexander-Whitney map to this, you get tensor products. And when you apply Alexander-Whitney over here, you get tensor products as well, and you should get the same exact stuff in the tensor products. So even if I get something different here, then when I apply this map, whatever the different, yeah. So kernel should be kernel of the Alexander-Whitney map of the image. How do I want to write this? Kernel of the Alexander-Whitney map of the image of acting on the image of cyan. Okay, I need to think about how to write this, but I think I said it properly. Just not sure how to formally write it. Any questions so far? So yeah, we're still kind of brainstorming. Yeah. I don't want to prove this right now or go into it too much, but also the A configuration stuff and this stuff are actually the same thing for like certain examples, like all the stuff in conjecture 1 that I wrote down before, however long ago, where we're that particular, if anyone has that in their notes, that particular incarnation of this problem, just the conjecture 1, for that you can actually just solve everything with A configurations. I mean, you still have to prove that everything works out, but you don't need this. Basically, this map and A configurations for those examples end up being the same thing. So these are very related if this does exist. This is like very close to this map. Yeah, and A configurations are just like this weird thing I defined in my thesis, but I can go into some examples in a second if we want. Any properties for tilde psi n? Yeah, I can go into what it is actually in a second. I just realized that whiteboard is duct taped. Well, yeah, it's not duct taped. Duct taped, yeah. No, the whole thing is the whole back of this though is like glue. So this is actually pretty heavy, the board. not like heavy, but like heavy enough where you need something to actually keep it up. This tape isn't even really like, yeah, see, it's not even like touching the wall. The tape isn't keeping it up. Okay, just trying to like decompress my brain for a second. But I think I've basically summarized at least not only the problem that we're trying to solve, but also the calculus that we're trying to use to solve the problem, and also outlining an argument to try to prove it. So it's like this two-step argument where we're basically breaking up this commutative diagram into like two diagrams and trying to prove each one is commutative separately. So famished. I broke my whiteboard somehow, so I'm back to the good pen and paper. Actually, I know gravity. Yeah, so Stuckey, do you have any questions? Do you want to call in at all, or are you too scared? Not scared, but like I know this stuff it's not. I know I'm leaving out a lot of stuff too, so even for you, I know this might be a little confusing. But yeah, that's why I want some input, because I want to focus on the most confusing aspect of it first. Rather more technical questions. Yeah. Join the Discord, sure. Yeah, I want to start getting into the more technical stuff, because I think the whole broad picture I've essentially sort of already painted the whole thing so far. Let me see if I can get you in there. Okay. Am I in there now? Wait. Okay. I think I'm in.
Oh, you got saved from the sound nightmare because I was muted. Okay. Excellent.
Is there any? Can you hear me? Is it good?
I can hear you. You probably can hear yourself again, but let me. That should be fixed now.
I can barely hear it. You sound good.
Okay. Well, should be over. Yeah.
So you wanted to get into some more technical stuff?
Yeah. So I have I put an Excalibur in the room.
In the Discord?
Sorry, in the the chat room for the voice channel.
Oh, okay. Let me try to
I never know how to describe this object.
Yeah, I don't know. I don't even know how to use this. Let me try to figure it out. Chat. Where's the chat? Or maybe, can you just put it in the general one? Maybe that's easier.
I can do that. Yeah.
I can't even find the chat.
Yeah, it's sort of obnoxiously well hidden.
Okay, cool. Wait, maybe I can share. Do you want me to share? Oh, this is your notes. Okay.
That seems like the the most sensible thing to do.
Let me try to share this. Okay. The only thing is this OBS. I was sharing on here and then it froze once. Like it just. Can you see this?
Oh, interesting.
In the stream? Because now I can't see.
Yes.
Okay.
But it looks like it's an outdated scene. You're not.
I'm not showing.
It's not showing what you are currently doing. Yeah.
Yeah, that's so weird. Yeah, I think there's just something wrong with OBS. Yeah, it's just frozen. See. Yeah. Oh. No. Yeah, I don't think I can show it. Okay. That's not good. I could write. So what's the question? Maybe I could just write it on the board.
Okay. Good luck. Actually, so here's what I'm actually gonna do. I'm gonna in Discord. I'm gonna share with you my screen.
Okay.
So that even if it doesn't come through, that you don't just have to like hear me shout symbols. Okay. This is gonna take
Yeah, sorry
a
about this.
minute. No worries,
I
no
don't.
worries.
I tried to update
Um,
OBS too, and I still don't think it fixed it. I actually like reinstalled it and everything.
don't go anywhere, please. Thank you, thank you, thank you. And we're going to share screen. Not going to share the whole screen. We're going to share that window. Okay. Hopefully that's visible to you. I really hope so, because I cannot move the mouse.
I only see.
Classic.
I just see your face.
Yeah, you'll have to click through. You'll have to click through.
Oh, wait. Maybe.
So there, there are now
okay.
3 of us in the
I see
Discord
it now.
call.
I see it now. Yeah.
Yeah. So my question is this thing going on in blue down here. So it's about the definition of the Schur homotopy.
Okay.
So in particular, so Rail is like, oh yeah, I think in both papers he's like, okay, here's how you do the homotopy
Yeah,
with two
he
things.
gives
But then
he gives the explicit definition with all of the S and D's, right? The S is the one
right,
that duplicates a number, and the D is the one that deletes one.
Yes.
Yeah.
So I see how the two the two chain version is, or that's not right, but
the two factors.
If there's 2 factors, I see how that is the same as the overlapping partitions. I'm happy.
Mm-hmm.
I don't see that extends to the 3-factor case. Because with the 3-factor cases is sort of obnoxious.
Yeah. Yeah, that's yeah, let me here. Can you see the board? Yeah.
I can see the board. Yeah.
You can see it on the stream, right? Or yeah,
yes.
I can't. I'm not doing it on the.
Yeah, it's fine. I think that amount of delay is acceptable.
Yeah, let me just go through the 3 case real quick, like in more detail.
Sure.
More formally. So yeah, I think you had written this out. You had some x, comma y, comma z, right? These are 3.
Yeah.
This is a simplex so these are all n simplices. So x is an n simplex, y is an n simplex, and z is an n simplex. So this is
correct.
A single simplex in C star m times m with coefficients in R. So yeah, when we take h of this, so it's going to be a sum. So really, like if we're being really formal, this is really an element. It's like x of 0, 1 through m, comma y 0 through m, comma z 0 through m. So then we're saying, okay, what is h of this? So this is when the Real paper, so he only defines it for 2 things, right? I think, in the paper.
He tells you how to do it for 3.
Does he?
But it's slightly less explicit.
Okay, I don't remember.
So I've written down what he says.
Well, we could look at it later, but yeah, I don't think we need to go into what he actually said. He did all that stuff like a long time ago, so any of his stuff might be a little out of date, or there might be like easier ways to write it either way. But so what the Schur homotopy says is you split the simplex, even if it's in a Cartesian factors. You basically count out the first number of vertices for each of them, though. So it's gonna break into 2 pieces. It's gonna break into x of 0 through I, comma y 0 through I, comma z 0 through I. So this is gonna be like the quote unquote like first piece, because the Schur homotopy involves splitting it into 2 pieces. The first one, you're not gonna do anything to it. And of course, this is gonna be like a sum over I, right? So I is gonna vary from 0 to m. so the first piece is just basically you can think of it as it's the first ith simplex in the Cartesian product. So it's actually the first ith simplex of each one. And then the second half, so you're going to have the second piece of this, which is from I to m for all of the x's, x, y, and z. And then you're going to apply the Alexander-Whitney map to that. So it's going to be Eilenberg-MacLane map of the Alexander-Whitney map of the x from I to m. Yeah. So Alexander-Whitney map of, I'll just write it like this, from I to m, y from I to m, and z from I to m. But the thing is, once you apply the Alexander-Whitney map to this, it's going to break this into more overlapping partitions, because this is going to like break into, you know, x from I to the second I, and then from y from that second I to the third I, and then z from that third I to the whatever the fourth index variable would be. Oh, well, actually, just till the end, to m for z. So yeah, you're basically gonna get a mess here, and this is why this problem is like so annoying, right? Because over here it's pretty straightforward. Like, we haven't done anything to this. You just apply the identity map to the left part. But on the right, we're splitting this up even further with this Alexander-Whitney map. And then when you apply the Eilenberg-MacLane map, that's just the shuffle map backwards. So then you end up with like a sum over all possible shuffles, and then you have, you know, you're shuffling 3 things together instead of just 2. So there's like even more things. But so do you want me to try to write down like a couple of the terms for this? Because obviously I can't write down all the terms. Even if m is like 4, I think it's already a huge number of terms. I could take m equals like 4 or 5, and then I could write down a few of them just so you get the idea, if you want. Or
so I'm wait, why is the Alexander-Whitney map in this part of the story?
Because that's what H is.
That just like
H basically says we split our thing into 2 pieces, and then we do nothing to the left, and then we apply the composition, which is not the identity in general, to the right half. Because we're trying to join these 2 things together. We're saying we have the identity map and we have this composition, and they're not equal to each other. But if I split everything up and then join it together, that's a homotopy that basically joins them.
okay.
So H, and I essentially not came up with this map, but like there was no notation for it, so I kind of had to like reason through what the best way to write it down was. So
in the usual.
So I ended up writing this like I came up with notation like something like you could
I see.
kind of write this down as like
So-
A1, A1, A1.
Oh, okay.
A2, A3.
I now understand why this
You
gives
starting to
the
get it?
overlapping partition description. Yeah.
So there'll be some overlapping partitions A1, A2, A3, A4, and if you kind of join them together here, then you're going to get this stuff. So another way to write this would be like this way. This is kind of like just notation I made up, but you see how the A1, A1, and A1, these are all the same? So that's corresponding to like 0 through I being the same for X, Y, and Z. So it's the same A1 for X as Y as Z. So A1, A1, A1. And then we get another partition from X, which is going to be A2 from I to whatever the next index variable is. That's going to be A2 here. But then because we're applying the Alexander-Whitney map, we actually end up with, we have another step here where we take the A2 part, but then we have an overlapping partition A3, and that goes in the second piece, and then that gets broken again into A4, and that goes in the last piece. And then I'm just writing it this way, but these would all be shuffled together. So, sometimes there's degeneracies here. Wherever there's a degeneracy here, there's like not a degeneracy in the other ones. But that just has to do with all these shuffles. So yeah, the problem with this notation though is, well, I guess there's not really a problem with it, but yeah. So this is like also a conjecture, but all of these things should be able to be written as some joins of these like AWEML stuff. So it should be like, yeah, basically there should be some sort of diagram we can write down like this that should represent this thing instead of having to write down every term, right?
Interesting. Okay.
It's all basically like notation. You just have to prove that the notation makes sense. That like this is actually like well defined and represents like what's actually being defined for H here.
Yeah.
Are you still confused about the map at all, or at least does the definition make sense, or are you still confused about like what?
So yeah, I still don't understand how Rail's definition is the same as this, but I'm
let's
perfectly
write down
satisfied with
let's write down
this
his definition then, and let's go over his then. So what's the definition he uses for 2 or for 3?
For 3. For 2, I'm satisfied.
Oh, 2 you're okay. Okay, yeah. Let's do the 3. Actually, so it's possible that you could also do this backwards. So it's possible he did it the other way. But yeah, this should be correct. Yeah. Is that the one that's on the screen that you had written down?
It is. Yeah.
Okay, yeah, let me just copy that. Okay, so H3. Oh, I think I know. I see. No, you have to be careful. Yeah, he's not defining the same H that we are. Yeah, it's a different H.
Okay. Okay.
Yeah, I had to struggle with this too. So there's another paper by, what's his name? Tonks, I think. And he goes into, there's like this whole giant cube of homotopies, and so there's like a lot of different choices, and so Real is like picking one of the choices, but I'm picking a different choice. So it's like really, but his choice is like not the best. My choice is better, just trust me. Because his choice is like, he's like trying to compose homotopies because he has a homotopy from M times M Cartesian product tensor with C star of M. So you can break off one factor at a time, and there's a homotopy for that, and he's composing all of those homotopies, but you actually end up getting a different homotopy than the one I'm using. So,
okay.
Yeah, I would just ignore that definition. Yeah, it's just not important.
Fair
it's
enough.
just there's this just that's actually one of the main problems with this stuff is that there's so many like homotopic things that are like not equivalent to each other, but like somehow the choice doesn't really matter in the end, and it's like because actually there's actually many of these H's, and you could define the graph homology stuff using any of the H's, and you should get an answer. You'll just get a different answer, but everything will still work out. Like, so it's kind of cool. But so there's essentially like a whole like space of different ways of solving this problem, but they're all like homotopic to each other.
Legit.
Yeah. So yeah, I mean, I think conceptually is probably the best way to understand the map though, is like you just split it into 2 pieces and then you apply the thing that you're trying to make homotopic to the identity. So you're doing the identity on the left and then you're doing the composition on the right, and we know that this is not equal to the identity, but if we do this homotopy, then it should repair the difference between the 2.
Sure. Okay, so the reason why this came up was because I had a lot of concerns about like the order in which terms appear. Some of those things have been resolved. Let me see if sort of having clarity on this H definition actually, or the H definition that we're trying to use answers my questions.
Does this notation make any sense to you, or is this confusing?
Yeah, this notation makes sense.
Okay.
Assuming you mean that like block notation. You wrote this thing that's on screen a couple of times in the past.
On your screen
I
or
like
my
this.
screen? Oh,
This
right.
makes a little more sense to me.
Right. Yeah, that's essentially the same thing. Right. Yeah, perfect.
Yeah, it's just I need the reminder that there are all these like that A2, A3, A4 are different sizes, but like the boxes are the same size because of these degeneracies.
Right. Actually, yeah, that's probably a better way to write it. So let me see. So it would be like A2.
It's this box is like after I've already applied 3, 2, 1. So like the actual box that you want.
Yeah, this is probably better, more explicit notation. Kind of makes it clear that there's like a bunch of degeneracies here. The only thing that you have to be careful to remember though is that
they're not ordered actually.
Yeah, that the A4 could actually be here, or actually could be split up. Like the degeneracies could be split up at any point here, and they're all shuffled together. So it's actually a sum over all possible shuffles of all the degeneracies.
Right. So the things that are actually ordered, the partitions, the parts of the partition are ordered.
Yes.
You can't screw around. Everything in A3 is bigger than everything in A2.
Right.
But then what gets shuffled is
where the numbers get repeated. So here, let me just write out like an example.
Yeah,
so you might
please
have like
do. Yeah.
0, 1, 2, 0, 1, 2, 0, 1, 2, and then in the part that's joined together, you might have 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, 5, 5, 5, 6, 6.
Oh, right. It's the shuffles, right? It's the shuffles that get, or excuse me, the degeneracies that get shuffled.
Yeah. So see when there's a jump in the numbering from like 2 to 3 here, that means that there needs to be a repeated number for every other factor. So if 2 goes to 3 here, this has to go 4, 4. This has to go 5, 5. 3 goes to 3 here, okay, then this one can go 4, 5, that's fine. But this one has to go 5, 5. Because all of the other ones, whenever there's a non-degeneracy here, all of the other ones have to have a repeated number. So this would be one of the terms. But of course, you know, for every overlapping partition, A1, A2, A3, A4, and for every shuffled set of degeneracies, we have a different term, right? And there's, you know, plus or minus for each one. So yeah, this would just be like one incarnation of one particular overlapping partition and one particular shuffle for the degeneracies of a term that follows like this pattern.
Okay, and so in the way that I've been writing this, the point is that each one of these columns is going to have 2 underlines.
And if you play around with this stuff, you'll probably even on your own, maybe you'll come up with even better notation than I have, you know. It's like a constant, as I get deeper into the problem, I like figure out better and better ways to write things. Which is
that makes
pretty
sense.
natural, right? But yeah, when I started out, I was basically writing everything in like this form with these A's, which is actually not too bad, but you need to make sure that it actually like corresponds to reality, which is like the hard part. Just because like these maps are just so messy. All the AW, EML, AW, EML, AW, EML, and everything's like joined together too, so Yeah, every time you apply an H, you get another join. So it's like this joins two things together. You apply another H after, you're gonna have like three things joined together, and it just gets more and more complex. But yeah, so the cyan map should include terms like this. It should be able to translate the stuff that I was writing on the left side of the board, all the operatic stuff. It should be able to translate that into these overlapping partitions in the Cartesian product, and it should make the diagram commute. So it should be, meaning that it should be giving us the correct terms, nothing like nothing else. Yeah, so like a term that looked like this, what would be the... So yeah, any of these we can actually write down the cyan map for these. These ones, as long as it's like just a join of two things, then it's fine. So actually, yeah, let me just explain how I even got to the like cyan from this. So I was trying to figure out like if we had terms that looked like this, right? Like I was just thinking hypothetically, like let's say we had terms that looked like this, what would the Alexander-Whitney map be of that, right? And you could think of any generalization where they were something else, right? So like what is...
Yeah. Real quick,
yeah.
the thing that you're saying about the terms that don't look like joins, this is an issue when like after the first round of these things, when you have different partitions in the first and second factor.
Yeah, that's when it gets
Is that
sloppy.
what we're concerned about? Okay.
Yeah, exactly. You'll end up with stuff like A1, A1, A1. Let's say I applied a delta map to this, right? Like, let's say I apply delta 2, 4. Right? So what would it look like after I apply delta 2, 4? I would have A1 on all of them, right? Because the second factor just gets duplicated. So yeah, I mean, everything's the same. I just get another row, but the second row gets copied to the fourth row. So it'll be A3 here, a blank, and then A3 here also, blank, and A2 is still here hanging out, and A4 is over here. Right, so delta map is nothing crazy. It literally just copies one of the rows. And now you have a new row, but it's like literally the same exact row. But then the question is, yeah, so now when I apply the she-map, now it's confusing because the she-map can split basically any of the blocks that are duplicated. So it's going to give us something non-trivial when it splits the A1s that are in all of them, and also now A3 appears in 2 and 4, so it's going to have to split that one as well. You can show if it splits on any of like the singular ones, you just get like degeneracies, so that doesn't give you anything special, but yeah, essentially if we just stayed in this world where everything was just A1s on the side and then we just had singular A's in each one individually, that's kind of like the conjecture 1, and in that case I think it's not so hard to prove what happens. But the harder stuff is, yeah, exactly what you were pointing out. Once you start having like multiple A's on the inside here, and it's not just multiple A's on the left, then it starts getting really messy.
I see.
Yeah. So what we want to be able to do is we want some cyan map that basically we can do everything on the operatic stuff, and then we just apply cyan and we get all of these terms. And that's exactly the terms that we wanted. And then when we apply the Alexander-Whitney of these, it's just the coaction of everything that we had before. But of course we have to prove that. That's the whole thing. Does that make sense though? At least like the like my plan of the proof?
Yeah.
Okay. Yeah, so all of these terms are like joins. They're like these joins of these EMLs of these basically stuff that we can write down as these diagrams. Um, but you need to be a little bit careful because I was a little bit too uncareful in my thesis, and I came up with these things called like A configurations, but I realize now that these things aren't A configurations; they're slightly different. Um, but basically, the general thing is, if I'm being a little informal, it's like we have a delta of a AW of an EML of something, and then we join it with another one, and then we join it with another one, etc. So basically, this is just another way to write this. But yeah, we want to show that all of the terms are like these are of this form where they're like the joins of these A's. And then it just becomes a matter of proving that this if the cyan map makes sense, then we can go from the operatic stuff to this stuff, and then applying AW should commute with that. Yeah, everything I was talking about before. Yeah, I was also trying to brainstorm maybe if there was a map the other way. I was thinking possibly maybe I had the maps backwards. Like maybe there was a way to go from this A stuff backwards into the operad and then get the correct answer that way.
I mean, like, maybe, but the proof in that direction is going to be nightmarish, right? Because then you're going from a polynomial number or an exponential number of terms to a polynomial number of terms. So you're really having to deal with the signs.
Right,
like,
right. Yeah, I think I reasoned out earlier that it didn't make sense actually, but yeah, I think you're right. I think what it would have ended up being, I thought like there was going to be just a bunch of terms that ended up canceling because there was like a plus. You know how there's like a big plus or minus in the EML, where you sum over all the partitions and then each different permutation gets a different sign. So there was like
right.
a shitload of signs, and I was just thinking, okay, maybe you, like one of the things maps to something, and then it just like goes plus or minus forever, like until you get to the end, and then you just get one term at the end. But I think I ended up reasoning that it didn't make any sense because I was trying to show that how do I write it out? So if the cyan map went the other way, the whole thing was trying to show that this Alexander-Whitney map, that this whole thing commuted, that I could go this way and then apply here and get into the tensor product stuff. I'm doing this really, really badly. So use your imagination. Back at the other board I had at the top of the diagram, we had a bunch of basically like M Cartesian factors here, and then we had this thing here where I had the operatic stuff, the BE stuff. So if the map went this way, the whole thing was trying to show that this commuted, but it wouldn't make any sense because a single simplex here, if I take the Alexander-Whitney map of it, I don't get an entire operation. I just get one of the simplexes of the operation. So I think it didn't make sense because if I went here and then applied here, I would get all of them, not just a single one. So there's no way to make this diagram commute that way. So yeah, I think it just didn't make sense to go this way. So we have to find the map that way. I think that's the only way it makes sense. Yeah, so if we can get this one that makes this whole thing commute, then we just basically, instead of going, so the whole thing is we go this way, then we apply Alexander-Whitney. If we prove this theorem, it would say we could just go up this way and then take table reduction here, and because we would prove that this commuted, then we would get the correct answer. So yeah, I think it's just a matter of basically translating this A stuff, or sorry, trying to come up with a map where all the operatic stuff is actually just keeping track of these A's, and then if we can do that, then that it basically becomes like a dictionary, you know, like computer science. Like if we look up any of the operatic stuff, any of those elements, it should be able to, there should be a map that basically tells us what the actual elements should have been, but we didn't have to compute them because we just used logic.
Right.
Yeah, because no one wants to deal with all these terms, right? There's just, I mean, essentially we know we're going to get surjections at the end, so most of these terms are going to be superfluous because once we apply the Alexander-Whitney map, a lot of them will just be degenerate. So we're sort of storing a bunch of extra terms for no reason, essentially. Yeah, any other questions I can help with? I mean, you're asking really good questions. Obviously, the Xi map is very important to get that down precisely.
I don't think so right now. Just got kind of hung up on this when I was looking at the exercise. So keep working on it.
Okay, yeah, perfect. Yeah, I think we'll end soon. Yeah, it's already been an hour and a half. Okay. I'm trying to think if there's anything I left out. So basically, we have these like joins of these EML stuff. That can be represented as these AI kind of joined diagrams. Then the question just becomes like, how do we take the Alexander-Whitney map of these, and when we take the Alexander-Whitney map, what surjections do we get? Well, we have to prove that the ones we get are the ones that come from the operatic stuff, and taking the table reduction. All right, I think probably summarizes everything. I've been missing chat a little bit. Oops, sorry. Just call it deconfiguration. Oh, Discord. Now open your streamer key, public key. Eric Matt B2B Saturday set. Yeah. Okay, yeah, I think we'll end it here. As long as if we don't have any other questions, I'm pretty brain dead. I think I wore out Stookie too. So all right.
I think I'm.
No more questions. Everybody good? I guess. All right. Well,
Yeah.
thank you, everybody. I'll drop the call now, I guess. Are we good?
Yeah, I think so.
Okay, cool. Thank you very much for showing up. Let me get out of here. Why is it asking me stuff? Get out of here, Discord. Okay, guys. Yeah, so this has been a Saturday research. We're getting this is, I think, the 5th one I've done. So been going for a little more than a month, and we're definitely getting somewhere. I think we're trying to figure out what the cyan map should be, and if we have this, I think that's sort of the key, but it may be hard to define. So if that becomes too hard, I have another backup plan that we've been sort of talking through. But yeah, still just brainstorming. It's a process, though. Math research is really hard. You basically have to bang your head against the wall until you start noticing like some patterns. You try to prove some. You notice some things about some simple examples, right? And then you try to, you see those patterns. You try to prove that they're true. So that's essentially how I've gone through this problem. I've done some smaller sort of examples where we have fewer vertices, where we end up with stuff that we can sort of make sense of this way with these AI diagrams. And then I've sort of tried to backtrack to the operatic side, like which type of operatic information would lead to this, and can you get the resulting coaction that you get from taking Alexander-Whitney map of something like this? Can you recover that information just purely from the operatic stuff using all that delta operatic Xi stuff that I was, constantly splitting up the board into left and right and comparing the two stuff we were doing. Okay, yeah, so I'll end it here. I'll put the video on YouTube. But yeah, thanks everyone for showing up, and I appreciate it. Let's try